This video contains the solutions to the parametric equations practice problems handout that was given in class. Please try to work through the problems on your own before watching this video to see the solutions. So in this one, we're given a parametric curve given by two equations, an equation for x and an equation for y, and we're asked what point on this curve corresponds to t equals 3. And all we have to do is plug 3 into those two equations. So to find the x-coordinate of this point, we plug in 3, and we get 2 times 3 squared minus 3. That works out to be 15. And then we plug 3 into the y equation, 4 times 3 plus 3, and that happens to also work out to be 15. So the point we're looking for is 15, comma 15. The value from the x equation goes in the x-coordinate, the value from the y equation goes in the y-coordinate. Now for the same parametric curve, we're asked for the slope of the tangent line to the curve at that point that we just found. So the formula that you need to know here is that dy dx, the slope of the tangent line, is dy dt, the derivative of the y equation, divided by dx dt, the derivative of the x equation. So first we're going to find the derivative of the x equation. So dx dt is 4t minus 1, and then we plug 3 into that. So dx dt evaluated at t equals 3 is 4 times 3 minus 1, which is 11. We're going to do the same thing for the y equation. Find the formula for the derivative of the y equation, which is just 4. And this is just sort of a technicality here, but when we plug 3 into that, again, we just get 4. And so the slope that we're looking for is 4 over 11. The y derivative divided by the x derivative. Now for these next few problems, we're actually being asked to come up with our own parametric equations. Now this one, since we're given an equation in terms of x and y, and that equation is solved for x, this is actually pretty easy. All we're going to do is we're going to let y equal t, and then x will equal the same equation that we already had, but with y replaced with t. So in this case, t squared minus 4. And notice that if we substituted y for t, we would get the original equation, x equals y squared minus 4. So whenever you have an equation that's solved for either x or y already, it's really easy to come up with a parameterization for that curve. So this is it, that's all we have to do. So for this one we need to work a little bit harder. This is a line segment, so there's a trick for this one. And the format for parameterizing a line segment, this isn't the only way to do it, but it is an easy way to do it. And it's that you have a 1 minus t and then a t for both the x and the y. And then in front of the 1 minus t, you put the starting x-coordinate, and in front of the t, you put the ending x-coordinate. And for the y equation, in front of the 1 minus t, you put the starting y-coordinate, and in front of the t, you put the ending y-coordinate. And again, the reason why this works is that if I substitute in t equals 0, the terms that just have a t in them are going to disappear, and the 1 minus t's are going to just become 1, because 1 minus 0 is 1, and so we get the starting x and y coordinates. And then at the end of the parameterization, when t equals 1, the 1 minus t's become 0, and the t's become 1, and so we end up with the ending x and y coordinates. So it's very important that we include here that the parameterization is only good for t between 0 and 1. That's an important part of the parameterization. We can't leave that out. Now what we can do, and this is the way that you'll often see these written in solutions, is we can simplify these equations. So for the x equation, we can distribute that 4 and get 4 minus 4t, which we might also write in standard form as negative 4t plus 4. And then for the y equation, we can distribute. We get negative 1 plus t plus 7t. And again, simplifying that, we get 8t minus 1. Now that's not necessary. The original answer that we had is correct, but again, if you're comparing this to solutions on the online homework or in your book, you'll see them simplified normally. Now for this last one, we're asked to parameterize a circle. And the thing that we need to remember here is that there's a standard parameterization for the unit circle. Now the unit circle is a circle of radius 1 centered at the origin. So the radius of the circle is 1, and the way that we're going to parameterize it is to let x equal cosine t and y equal the sine of t. And what we're recalling back to is that in trigonometry class, when we had a point on that unit circle, connected to an angle here, and here the angle is what we're calling t. We called it theta back in trigonometry, but it doesn't really matter what the variable is called. The coordinates of this point are the cosine of t, comma, the sine of t. And so we're using that knowledge from trigonometry to parameterize this circle. And again, that parameterization is only good for t from 0 to 2 pi. If we go beyond 0 and 2 pi, then we just start looping around the circle multiple times. So if we just want to parameterize the circle, we only need to go from 0 to 2 pi. Now, this is the circle of radius 1 centered at the origin. So we need to modify this in two different ways. We need to make the radius be 5 rather than 1, and we need to make the center be 3, 4 rather than 0, 0. So the way that we make the radius 5 is by multiplying both the x and the y coordinates by 5. So this right here is the circle of radius 5, but still centered at 0, 0. So that's not our final answer quite yet. But one more modification is going to move that circle over 3 and up 4. And we do that by simply adding 3 to the x-coordinate and adding 4 to the y-coordinate. And again, we note that our parameterization goes from 0 to 2 pi, and all of that together is our answer, is our parameterization.